Hi everyone. Today we are going to be talking about angles, azimuths, and bearings. So all of this material for the engineering surveyors is in chapter 7 of the textbook. And for the practical surveyors, if you take a look at your textbook, that would be in chapter 6. So we'll talk about chapter 5 and chapter 6 from practical surveying and chapter 7 from engineering surveying. So I've posted to the internet some notes from this lecture, and I've also posted your homework assignment. So please take a look and we'll follow along with that when we do this screencast. So the first thing that we need to talk about when we discuss the idea of angles and angular measurements is in surveying, we sort of divide the world up into two planes. One of the planes is vertical and the other plane is horizontal. And if you think about it, that's if you're familiar with coordinates, that would correspond to x and y and z, where xy would be the horizontal plane and then z would be the vertical axis. But we really think about it in terms of a vertical plane rather than a vertical axis because you can turn that plane in any particular orientation. So by defining the world in terms of x, y, and z, we can find or identify the location of any point in any space from the other point. So the picture on your screen right now, figure 7.1, talks about either sort of an angle, either in the vertical or in the horizontal. But let's talk a little bit about vertical since we've been using a level. Now with the level, we've been talking about vertical distances. And for those of you that have had trigonometry, you can probably suspect that if you have a disk slope or along a horizontal line, if you have an angle of a particular line with the horizontal, that you could also determine the vertical distance. So when we talk about angles, whether we're talking about vertical angles, which we'll discuss specifically in just a moment, or horizontal angles, we have to specify where we're referencing from. So in other words, where is our zero and which way we are turning toward. So are we turning to the right, to the left? Are we turning in a different direction? But we always have to reference that. So we need to make sure that we always have a reference in terms of we need to specify what our reference is. So the next slide, this is sort of this is a really nice compilation of some of these ideas. If you notice, pointing straight up, which we might call the Z direction, is the zenith. And zenith just means pointing straight up in the sky. Now zenith is determined, if you look at this picture, by being opposite or 180 degrees off of, it's called the nadir or nadir, pointing straight down. So what you do to determine straight down is you can just take a string and hang a weight on it, and it will always point toward the center of the earth in the absence of incredible magnetic anomalies. So you can always determine down or nadir based on a plumb bob, and zenith is 180 degrees up. The other way that you can do this is you can level something. If you have a level bubble, a level vial, a level instrument, that will give you a horizontal line, and zenith will be 90 degrees off of the horizontal line. So some of the ways that we measure angles from the top of the sky, the zenith, a zenith angle is just measured straight down. So in other words, if you have your zenith angle, if you're pointing straight up, would be 0 degrees. If you're coming straight over to the horizontal, it would be 90 degrees. And if it were farther away, it would be more than 90 degrees. The other way to measure it is from the horizontal line, and this is called a vertical angle. If it's up from horizontal, that's called an angle of elevation or a positive angle. And if it's down, it's called an angle of depression or a negative angle. So these are just different ways to think about angles. But the important point is you always need to reference what your angle is. The other thing about zenith angles, this is drawn turning counterclockwise. you can also turn zenith angles clockwise. So you need to make a point of which one of those you're referencing. So once again, they're all sort of the same, but they are all the same information. However, we need to make sure that we understand what our reference is, where we're turning from, and which way we're turning to in order to determine that angle. Now, when we start talking about the horizontal plane is divided up into different, they're called cardinal directions. So north, in the case of if you're in the science and math building, if you're sitting in room SM120, which is where our class is, if you look out the windows, you are looking essentially north. There are different types of north, and we'll talk about this in a little bit as well. But what we're discussing when we talk about north, if we don't specify something about it, we're really talking about true north or astronomic north. That is not the north that you will get if you use a compass to try to turn an angle. And we'll discuss that in just a moment as well. But however, what you do get is a direction that is based on the poles of the Earth. Now, the picture that I have up on PowerPoint right now shows how to find a star called Polaris, or the North Star. If you look into the sky, if you're in the northern hemisphere, if you can find Polaris, you can, wherever you are on Earth, because Polaris is very, very far away, wherever you are in the northern hemisphere, if you find Polaris, you will always be looking north. This is not true in the southern hemisphere, and there's no analogy in the southern hemisphere. Navigation in the southern hemisphere of our planet is much more difficult. They use a constellation called the Southern Cross, and although I won't make you learn it, if you look it up on the internet, if you look up navigating by the Southern Cross, you'll find it to be very, very fascinating. It's a very interesting process. Anyway, Polaris, or the North Star, is not really north. It's an astronomic trick. It's the position of our world and the apparent position of the star Polaris that for several thousand years in the past, several thousand years in the future, will appear to be north of the northern hemisphere of the world. But how do you find Polaris? It's very important to be able to find it because it makes it easy to determine north. Well, this constellation is called Ursa Major, which is also known as the Big Dipper. And any of you who have seen the Big Dipper will see that it rotates through the sky. So in other words, this orientation of the Big Dipper will change throughout the year. So at one point it will look like this, and then it kind of rotates around, the tail's up and the cup is down, and then opposite down here, tail's up and cup is down during the calendar year. But whenever you find Ursa Major, or the Big Dipper, if you find the edge of the dipper and you come straight out from it, you'll see Polaris, the North Star. It's also in a constellation called Ursa Minor, or the Little Dipper, or the Little Bear. Ursa actually means bear, but in the United States we've decided that it's more of a dipper than a bear, and I could not agree more. So if you find the North Star, you will know where true north or astronomic north is, and then you can take survey readings from that. Okay, so here's just another indication. If we have up and north, we have a zenith angle, and we have a vertical angle, or an elevation angle, and then here we have what's called an azimuth. If you look in the plane, this is called the compass rose. And I'll draw this again. It's in your notes. So if you refer to the notes that are along with this diagram, the compass rose shows north, south, east, and west. And an azimuth is measured from north in a clockwise direction. The abbreviation for azimuth angle is AZ. And so the azimuth angle can be as little as 0 degrees, or as great as 360 degrees, and actually 0 and 360 degrees are exactly the same. They both mean true north. In this schema, east would have an azimuth angle of 90 degrees. It's called a north azimuth. south would have a measure of 180 degrees north azimuth, and true west would have a measure of 270 degrees of north azimuth. Okay, now this is related to and directly translatable into bearings, but bearings are only based on a single quadrant. So if you have an angle of bearing, the measure is between 0 and 90 degrees, and the designation of which quadrant you're in, whether it's northeast, southeast, southwest, or northeast, is also given. So as an example on the notes that I've included with this lecture, if we had an azimuth of 280 degrees, a north azimuth of 280 degrees, between 270 and 360 degrees is going to be in the northwest quadrant. So it means that we are 10 degrees further along in the arc than true west. So that means that we're in the northwest quadrant. And the angular measure from the north, we always measure bearings from either north or south. You do not measure bearings from east or west. But we're 10 degrees from west, so that means we're 80 degrees from north. So a north azimuth angle of 280 degrees corresponds to a bearing of north 80 degrees west. And there are some homework problems that will reinforce this, especially for the engineering surveyors. Now this is a slide that may be of interest to the engineers as well. It's something that the practical surveyors should know, but you're not going to be called upon to do this math. If you have an angle, now this would be an angle of elevation, wouldn't it, of 18 degrees, you can calculate, we have a slope distance, a horizontal distance, and a vertical distance based on this angle and any one of these three linear measures. Now you did something similar to this in our lab where you measured the grade on the ADA ramps. So you use the theorem of Pythagoras, which is really another way of expressing these ratios of angle to side, and the ratios are just called either tangent, cotangent, or excuse me, tangent, cosine, or sine. There you go. And or the cofunctions, which would be the opposite of those, the inverses of those, I should say. So this can just give you an idea of the relationship of what the cosines, sines, tangents, horizontal distances, vertical distances, and slope distances look like. Here's another way to measure angles. If you have a closed traverse, what a closed traverse means is you are surveying points in succession and coming back to the first point that you started at. That's also called a geometrically closed traverse. There are other ways to close traverses. If you know the beginning point and the ending point, you can have a mathematically closed traverse that isn't actually a closed shape. But in a geometrically closed traverse, point A is where you start and point A is where you end. And if you have a geometrically closed traverse, the angles that are being shown measured here are all called interior angles, because you're measuring, if you started here at point A, you start and you measure the angle at A that has A as the apex, the angle that B is the apex, and so forth around the shape. Now, if you look at these are called horizontal angles to the left, horizontal angles to the right, because you would sight here and turn to the right. So this is called a horizontal angle to the right. In example B, if you take a look at point A, what you see is you're starting, well, they're both, I'm sorry, I am mistaken. Those are both horizontal angles to the right. You can, if you turn the other way, if you started here and turned this way, it would be called a horizontal angle to the left. So horizontal angle to the right is referred to as HAR. Horizontal angle to the left is referred to as HAL. You can also measure exterior angles, and something that we'll look at in just a minute called the deflection angle. And they're all going to give you the same information. As you can see here, whether we measured a horizontal angle to the right or horizontal angle to the left, the number is going to be the same. But when you're actually taking the shots, it's important to remember which direction you're shooting in. Now, for any closed traverse, the sum of the angles will add up to a specific number depending on the number of sides. So if you take the number of sides of a closed traverse, you subtract 2 from that number and then multiply it by 180 degrees, that will give you the sum of the interior angles of that closed traverse. So that means if you have a triangle, which is 3 sides, 3 minus 2 is 1. 1 times 180 is 180. It means that the angles of a triangle, the interior angles of a triangle, will add up to 180. For a rectangle or a quadrilateral of any sort, there are 4 sides, so 4 minus 2 is 2. 2 times 180 is 360. So the interior angles of a rectangle will always add up to 360. And if they don't, if your measurements say differently, then you need to adjust that error. It goes back for the engineering surveyors to some of that least square stuff that we did last time. Although we're not really going to spend a lot of time doing this in class, it's important to note that you can't say every pentagon in the world has the same number of degrees except for mine, and mine came out 2 degrees higher. You have to adjust that error back in a logical way so that your answer comes out to be geometrically correct. And once again, getting back to the error theory, if the error is too great, you have to redo. If the answers are not good enough, you have to go back and redo the traverse to get answers that are good enough. So here's an example of deflection angles. What this means is that if I started here at point A, if I had gone straight 180 degrees through point B, that would be the line that I'm measuring from. So if I turn this way, that's to the right. That's a deflection angle to the right at B. And here at C, I go beyond C, and now I'm turning to the left and again to the right. Now, this sort of a traverse from A to B to C to D to E might be the sort of thing that you would set up for a simple roadway. Now, with roads, of course, you have curves, but this may be, maybe it's a fence going around an oddly shaped pasture where you start at point A, B, C, D, E. And you're not really getting around. So let's say it's between a rock wall and the side of the barn. Okay, so the rock wall's here, side of the barn is here. You need to put up a fence. So it's not geometrically closed, but if you know where point A is and where point E is, in other words, where you need to start, where you need to end, that could still be a mathematically closed traverse. And sometimes expressing angles as deflection angles is a better way to do it. So what you use really depends on the situation, the applicability of whatever type of angle you have to that particular situation. All right, so here we have a reference meridian, like here we have north, and we're talking about azimuths, right? So line D, we spin around 330 degrees. Line C, we spin around 235 degrees, and so forth. But the way that we generally compute azimuths is from north in a clockwise direction. Oops, and here's bearings. So once again, here we have a 70-degree angle between north and line A, line OA. That means that the bearing of line OA is north 70 degrees to the east. Line B is south 70 degrees to the east. Line C is south 55 degrees west. And OD is north 30 degrees west. Once again, you always reference from north or south. You never reference a bearing from east or west. Okay, this is something beyond the scope of what we're going to do in this class, but if you have bearings of lines, you can use this to compute the interior angles. And if you're interested, I'll be happy to discuss it with you. It's kind of interesting, but it's complicated, takes a lot of math, and takes a lot of concentration. So you can use it, you can do this with very simple computer routines. So I'm not going to make you do it by hand. Okay, this is just a compass. And one of the things that you notice is that most compasses are not oriented north is not true north. North is magnetic north. It turns out that there's a big magnetite body that is not at the North Pole, but it is south and somewhat east of the North Pole, or west of the North Pole. Anyway, what ends up happening is that magnetic compasses are actually attracted to that body. So what we do is we know where true north is, which is sort of the same everywhere. Magnetic north varies a little bit and it actually moves. But if we know the difference between those two, which is called the magnetic declination, we can calculate true north from readings that we take with a magnetic compass. And here in Powell, Wyoming, that number, the magnetic declination currently is about 14.5 degrees to the east, which means, here's a map, here's about where Powell, Wyoming is. You can see if I was right here at the intersection of Montana, Wyoming, and Idaho, that the magnetic declination was about 15 degrees, so we're just a little bit shy. The solid lines show the declination. In other words, the difference between true north and magnetic north. You see right here up the Mississippi River Valley, the magnetic declination is 0 degrees, meaning that, once again, it's sort of a geometric or geological, an earth-centered trick, let's put it that way, that on that line, if you keep going north, that magnetic north just happens to line up with true north, which is determined by the pole of the earth. So that is a line without a change in angle, and that is referred to as the agonic line. So the agonic line is essentially up the river, essentially coincident, I guess would be the best way to put it, with the Mississippi River Valley, or let's just say with the Mississippi River. So if you start out here, this would be Louisiana, this would be Alabama and Arkansas. No, this is Arkansas. So we have Mississippi and Alabama. And you start here and you go up through Tennessee, Kentucky, and this would be Illinois, and on up through the little wingding here in Minnesota, that you would not have to correct at this particular time for the difference between magnetic north and true north. But over here, we have about 15 degrees, 14.5 degrees to the east. In other words, if you take a shot, our true north, we're going to be looking at a place 14.5 degrees farther away in the opposite direction. And that's actually why, if you look at compasses, if this is north and south, you can see the east and west are reversed. And it's because of that, what you're reading versus what's going on the earth. So our declination is 14.5 degrees east. Okay, this is just a little a little computer program. These are available all over the place, but basically you can put in your latitude and longitude and create a data file and keep all this data stored if you want to. So here is a type of problems that the engineering surveyors are going to be working on. This is a case where we have a line of true north and we have a declination. In this case, what this is saying is that magnetic north is 3 degrees and 15 minutes to the west of true north, or it was at the time, because if you go back to this slide, if you notice the dotted lines show you by how many minutes the declination changes per year, which is really strange. But so magnetic declination is also changing per year. What that means is that if you have a survey that was done 100 years ago, magnetic north then and magnetic north now are not the same. So we need to know how much of a difference there is in order to base everything on true north and establish, in this case, property lines. So what we always do, and I will work a problem like this for you either on this vlog or in class, but basically you always draw your compass rose north, south, east, and west, and I always like to draw it orthogonal to true north. Then I place with a slightly lighter meridian line, I place magnetic north either at the time or now, and then I work from there. So in other words, the fact is that magnetic north in the past and in the future, magnetic north changes with time. True north does not change with time. So if you use true north as being the straight up and down line, true north, straight up, true south, straight down, you can always reference magnetic north as it moves from that true north. So my advice to you is to keep true north pointing straight up and working around that. So then if you have a magnetic declination in the past, you can find true north based on that magnetic declination. And then if you have a different magnetic declination now, you can still say, okay, true north is still true north, so my true bearing or true azimuth is the same. And then you can put in your new meridian and see what your new angles look like. And this is just a case where that happened. What they're saying here is that in 1878, we had a magnetic declination in a location of 4 degrees 30 minutes east. And here in 2000, we have a magnetic declination, I'm sorry, in 1878 it was at 7 degrees 15 minutes to the west. And now it's at 4 degrees 30 minutes to the east. So if we have magnetic bearings from 1870, we measure from that to find out where they are. And then we sort of backtrack that to true north, and then we can move forward to the year 2000. So I'll actually go ahead and work this problem for you. If you're in practical surveying, you're welcome to listen for a few minutes, or you can fast forward through this. I'm starting this at 26, 27, and it'll probably take about a minute. So this is going to be in your notes, but I mark true north and I mark magnetic north in 1878 as being at 7 degrees 15 minutes west. Okay, then I mark magnetic north in the year 2000 as being at 4 degrees 30 minutes to the east. All right, so the question is, if I have an angle, I'm kind of backing the question out. If in 1878 my magnetic bearing was 26:15 north by east, so a bearing of north 26 degrees 15 minutes, and I have these declinations, what is my true bearing and what is the bearing in 2000? Okay, so I can answer both of those questions. So if you look at this problem, what you see is that the line AB is 26 degrees and 15 minutes off of the 1878 magnetic bearing. We're closer to true north by this declination amount, which is 4 degrees 30 minutes. So if I take my magnetic bearing in 1878, which is 26 degrees 15 minutes, and I subtract from that the declination. Now you may have to add or subtract, so that's why you have to draw the picture to decide if you're closer to true north or further from true north. So I'm going to subtract the declination at that time, which is 4 degrees and 30 minutes. Okay. Now the thing is, when I subtract that, I have 15 minutes subtracting 30 minutes. So I need to borrow a degree from 26, so it becomes 25, and I borrow it over into my minutes column. But there are 60 minutes in a degree, so I borrow 60 and add 60 to 15, that becomes 75. So 26 degrees 15 minutes can be awkwardly written as 25 degrees 75 minutes, but now I can subtract 30 from 75 and get 45 minutes, and subtract 4 from 25, which is 21. So that means that my true bearing is going to be 21 minutes and 21 degrees and 45 minutes, and I'm in the northeast quadrant. So my true bearing is north 21 degrees 45 minutes. Now, to find my magnetic bearing in the year 2000, I refer back to my picture again, and I see that my line AB is closer still to the magnetic North Pole in the year 2000. So in this case, I'm going to subtract off that number again. So I start with my true bearing, 21 degrees 45 minutes to the east, and I subtract off the current declination. And I apologize. I'm going to go back. The declination originally, I wrote down the 430, but it was 7:15. So I'm going to take 26 degrees 15 minutes, and subtract from that 7 degrees 15 minutes to the west. And so my true bearing is 0 degrees. I don't have to do any of that borrowing stuff, but it's 19 degrees. It's north 19 degrees east. And I apologize. What I did was I picked up this number for this declination, but as you can see, this number goes with the current declination. So I'm changing that. Okay, so my true bearing is not north 19 degrees east. And now I am closer still, but this time I'm closer by 4 degrees. So I'm going to say 19 degrees 0 minutes to the east. And I'm closer still by 4 degrees and 30 minutes. So this is where I'm going to do the borrowing. I'm going to turn this into 18, the true bearing into 18 degrees and 60 minutes. Subtract from that 4 degrees 30 minutes. So 60 minus 30 is 30 degrees, 30 minutes, pardon me, and 18 minus 4 is 14 degrees. So that tells me then that my magnetic bearing in 2000 is north 14 degrees 30 minutes to the east. And these notes, you can follow along from the notes that I posted on the Moodle page. All right, well, that's it for today. The homework is posted. This homework is due sometime in March after spring break, so you can get started on it. And if you have questions, let me know. See you in class.